Hello, I am P3 TLP. Now I explain second chapter of elastic properties of materials, that is the bending of beams. Under this chapter, we will study neutral surface, neutral plane of a beam, derivation of expression for bending moment of a beam with circular and rectangular cross section, single cantilever, derivation of expression for Young's modulus. Okay, so now I'll go for the definition of beam. What is beam? A homogeneous body of uniform cross section whose length is large compared to its other dimensions is called a beam. So I can draw a beam like this. This is one homogeneous body. It has got several dimensions such as length, breadth, thickness, etc. But length of this body is large comparing to its thickness, then breadth, etc. So that's why this body is called as beam. So different types of beams are there. One of that beam is a single cantilever beam. So single cantilever beam is shown here. This is that diagram. A beam whose one end is fixed and the other end is free is called single cantilever. So this is that beam. One end of the beam is fixed here. This is that fixed end and free end is this. So that's why this beam is called as a single cantilever beam. Next concept under this, neutral surface and neutral axis. Now I will go for neutral surface. The beam is thought of as made up of number of parallel layers A, B, C, D, E, F, etc. It is shown here. A, B is there, C, D is there, E, F is there. And each layer is made up of parallel longitudinal filaments or fibers. That is not shown here. You have to think like this. AB is a layer. Layer is made up of number of parallel filaments. If a load is attached to free end of the beam, okay, consider this is that free end of the beam, the successive layers along with the constituent filaments are strained. A filament like AB, consider one filament AB here of an upper layer will be elongated to A dash B dash. So A dash B dash is shown here. This is elongated filament. And EF of lower layer, so this is that EF, will be contracted to E dash F dash, contracted. But the layer CD does not change its length. CD, middle layer, it does not change its length. Such layer is called as a neutral surface or neutral plane. And the filament of that layer is called as neutral axis. So we can take filament of this layer as neutral axis. That layer itself is called as a neutral surface. Now we'll define that. Definitions are given here. Neutral surface is that layer of a uniform beam which does not undergo any change in its dimensions when the beam is subjected to bending within elastic limit. Then neutral axis. The axis of the beam lying on the neutral surface is called as neutral axis. Okay, neutral surface and neutral axis both are shown here. This is that neutral surface. Okay, in that neutral axis also shown. Now I'll go for next concept, restoring moment and bending moment. When a uniform beam is bent, the forces of reaction develop in the body of the beam. Forces of reaction as shown here. Forces of reaction. These forces develop inward pull towards the fixed end for all layers above the neutral surface and outward push for all layers below neutral surface. So this force of reaction gives inward pull like this. Okay, and this force of reaction gives out a outward push like this. That means equal and opposite push and pull will be there. which is directed away from the fixed point. So this is directed away from the fixed point. These two forces develop a couple called restoring couple. These two forces develop a couple called restoring couple. So restoring couple is due to forces of reaction. These two forces of reaction. So the moment of restoring couple is called as restoring moment. So this is the definition for restoring moment. Similarly, due to applied force, we are applying force here. There exists another moment that is called as bending moment. The moment of applied couple, due to which beam undergoes bending longitudinally is called the bending moment. So two types of moments you have to remember. One is restoring moment. Restoring moment is due to forces of reaction. Another one is a bending moment. Bending moment is due to applied couple. Now we'll derive an expression for bending moment of a beam. Consider a long uniform beam whose one end is fixed and the other end is loaded. So you have to consider this beam. Imagine this beam. One end is fixed and another end is free. Free means it is loaded with a certain weight. Let A dash B dash be the elongated layer. So elongated layer after it is loaded. This is that elongated layer. E dash F dash. It is also shown here. E dash F dash be the contracted layer. And CD is the neutral surface. Already it is explained, middle layer, that is a neutral surface. Let R be the radius of the circle. R, capital letter R, is the radius of the circle to which a neutral surface forms a part. So from that neutral surface, that radius is taken. Okay. And theta is the common angle subtended by the layers of the common center O of the circles. Common center is O. And theta is a common angle. Now, we have to derive an expression for bending moment. We'll see the geometry of the diagram. So, according to the geometry of the diagram, angle theta is equal to CD. CD is the neutral surface, CD by R. R is radius. Therefore, we can write CD is equal to R theta. Theta and R already explained. Next, change in length. Change in length is equal to A dash B dash. That is, increase in length is A dash B dash and original length is AB. So, increase in length minus original length is a change in length. So, we can write AB is equal to CD because length of AB is equal to length of CD, that is equal to R theta. Because CD already we got that as R theta. So, AB is also R theta. Next we want A dash B dash. So A dash B dash is equal to R plus R of theta, where that small letter R is the distance between any two layers. Therefore, change in length is equal to increase in length, that is R plus R of theta plus minus R theta. So we get by subtracting that it is equal to R theta. So original length of the beam is AB is equal to R theta. So linear strain definition we know, it is the ratio of change in length to original length. So change in length is R theta divided by original length is also R theta. You cancel theta. So we get linear strain is equal to R by R. Next, we'll write a definition of Young's modulus. Young's modulus is the ratio of longitudinal stress to linear strain. Or rewriting that equation, longitudinal stress is equal to Young's modulus into linear strain. So Young's modulus, linear strain we have calculated. Okay, so linear strain is equal to R by R. It is shown here. This is linear strain. That by substituting that here. So that is linear strain R by R. So longitudinal stress becomes Y R by R. But stress, according to the definition of stress, it is restoring force per unit area F by A. So we have equation for longitudinal stress and we have equation for general stress. So compare these two equations. Equation 2 and 3 we have to compare. Then we can write F by A is equal to YR by R. Again rewriting that we get F is equal to YAR by R. Therefore moment of force about the neutral axis. So moment of force or bending moment is the force into perpendicular distance from the origin. So F into its distance from the neutral axis. So this is equation for a moment of force or bending moment. It is given here. So let's take this distance as small letter r. F equation we have. F is equal to YAR by R. Substitute that here. So substituting both for F and multiply that by R, we get YAR square by R. So this is for a neutral surface. Now we'll consider different surfaces in a given beam. That means moment of force along the entire beam. Summation of YAR square by R. That is equal to Y by R summation of AR square. Now we take summation of AR square as Ig, and Ig is called as moment of inertia. K is the radius of gyration about neutral axis. So moment of force is equal to Y by R. Instead of summation of AR square, we write that as Ig. So moment of force is also called as bending moment. So we rewrite that as bending moment is equal to Y by R of Ig. Now we'll substitute for Ig. Ig is different for different beam. It depends upon shape of the beam. Suppose if beam is of rectangular cross section, then Ig can be substituted as BD cube divided by 12, where B and D are breadth and thickness of the beam respectively. Similarly for circular cross section. So for circular cross section, we write Ig as pi rho to the power 4 divided by 4. It is given here. Y by R is constant, remaining terms we have to substitute, where rho is the radius of the beam. So according to the shape of the beam, dimension of the beam, that bending moment formula changes. Okay, now we'll take one expression, that is expression for depression produced at the loaded end and Young's modulus. Two expressions we write. For single cantilever. So already I have studied single cantilever is a beam whose one end is fixed and another end is free. And that free end is loaded with a certain load of W. Now we'll see this geometry of the diagram. Length of this beam is L, fixed at M. This is fixed at M. Total length is taken as L. So here to here it is L. Let a load W act on the beam at N. So W is acting on a point N. As a result, beam bends. So here beam bends. We get a depression in the beam. Two depressions are given here. One is Y0 at N. Another depression is Y at P. Consider a point P. Consider this point P on the free end at a distance x from the fixed end. So distance of this point P is x from the fixed end, and distance is L minus x from N. From N, L minus x distance is there for that point P. Let P dash be its position after the beam is bent. So while it is loaded due to depression, point P changes its position to P dash. It is shown here. Now we'll write according to the definition of bending moment or moment of force. So bending moment is equal to force into perpendicular distance. So here force is W. That W is equal to F, that is equal to mg. You can write like that. So perpendicular distance from N is L minus X. But bending moment of beam just now we have derived, that is Y by R of Ig. So compare these two equations now. Two equations for bending moment. Comparing that and rewrite that. Y by R Ig is equal to W of L minus X. So here again rewriting this. Take Y and Ig to right hand side. It comes to denominator of right hand side. So left hand side becomes only 1 by R. If Y is the depression of the point P, then it can be shown that 1 by R is equal to d square Y by dx square, where R is radius of bending, dy by dx is slope. Now you substitute this equation 9 in equation 8. In the place of 1 by R, you have to write d square Y by dx square. Substitute this here. So substituting that, we get this equation. In the place of 1 by R, we have written d square Y by dx square. So or rewriting that, d by dx is taken outside. So d by dx of dy by dx, that is equal to right hand side. Right hand side is the same. Nothing we have changed. Again take this dx which is there on the left hand side to right hand side. So multiply that L by dx, again x by dx, like this. Only d is kept here. D of dy by dx. Now integrate this. Integrating this, integration of d of dy by dx is dy by dx. Then integration of right hand side. So w by y ig is taken outside the bracket and integration of L dx is Lx. Similarly, integration of x dx is x square by 2 and constant of integration is C1. Okay, to remove that constant of integration, we have to take certain conditions. When x is equal to 0, at m, slope of the tangent is equal to 0. So, we'll go for the diagram. At x is equal to 0, this is that x. X is 0 means this is that point m. Here slope doesn't exist. Slope exists only here. So, at m, dy by dx is equal to 0. So, we can rewrite that. When x is equal to 0, that is at point m, dy by dx is equal to 0. So, substitute that in equation 10. Equation 10 is this. So, dy by dx is 0. X is also 0. That time C1 becomes equal to 0. So, C1 becomes equal to 0. Again, rewrite that equation 10 by removing C1. So, we have dy by dx is equal to w by yig of Lx minus x square by 2. Here again take that dx to right hand side of the equation. So, here it is written. Again integrate. So, integral of dy is y. It is a y. That is equal to w by yig. L integral of Lx is Lx square by 2. Similarly, integral of x square is x cube divided by 3. 3 into 2 is 6. Plus C2, it is a constant of integration. Again, to remove constant of integration C2, another condition we have to take. At x is equal to 0, again y is equal to 0. What is y? Y is a depression. Depression does not exist at m. At m, x is equal to 0. So y is also equal to 0. So substituting that in equation 11. So here you substitute x is equal to 0 and y is equal to 0. That time C2 becomes equal to 0. So again rewrite that above equation. Equation 11 can be written like this. At the loaded end, y is equal to y naught and x is equal to L. We'll see that. At the loaded end, this is loaded end, y depression y is equal to y naught and x is equal to L because total length is L. So we'll substitute that y is equal to y naught. Instead of y, we'll write that as y naught. Instead of x, here x cube is there, x square is there, you write that as L cube. Okay, like that. So depression produced at the loaded end is, simplify this, we get y naught is equal to WL cube divided by 3y Ig. Where W is load, L is length of that cantilever, Y is Young's modulus, Ig is moment of inertia. Next we substitute for Ig. For a beam of rectangular cross section, Ig is BD cube by 12. Substitute that here. Ig is there in the denominator, so 12 goes to numerator here, BD comes to denominator, BD cube comes to denominator. So at the end, we write Young's modulus equation as y is equal to 4WL cube divided by y naught BD cube, where y naught is the depression produced. We can rewrite this equation for y naught also. So if you cross multiply this, we can write this equation for y naught. Y naught is equal to 4WL cube divided by y BD cube, which is expression for depression. Now this is expression for Young's modulus. Now we'll go for types of beams. There are several types of beams. First one, simple beam, is a bar resting upon supports at its ends. Two supports are given at its ends, so it is called as simple beam. Then second one, continuous beam, is a bar resting upon more than two supports. So here three supports are there, so it is said to be continuous beam. Then cantilever beam, already I explained, it is a beam whose one end is fixed and the other end is free. So this end is fixed, this end is free. And fixed beam, a beam is fixed at its both ends, is called as a fixed beam. It is fixed here, here also it is fixed, it is said to be fixed beam. Then single overhanging beam, it has two supports are given here, hinged at one end, roller at other end, here roller is there, and overhanging portion at any one end of the supports. This is that overhanging portion, only one overhanging portion is there, that's why it is said to be single overhanging beam. So last one is double overhanging beam. This type of beams will have overhangs at both supports. So here also overhanging portion is there, here also overhanging portion is there, then it is said to be double overhanging beam. Okay, now we'll go for application of beams. Beams are used in the construction of platforms, as a support in elevators, as a support in aircrafts, in the framework as a truck beds, as girders in the construction of buildings and bridges, in the fabrication of trolleyways, in railway tracks as I-section beams. So different types of beams are used for different purposes. So some pictures are given here. This is a girder. Different girders are given. This is only one girder. Here 5 girders are shown. And truck bed. So here beam is used for a truck bed like this. And this is I-section beam.